Hey everyone, this is Connor Mead with the Calculation Center with another video in our calculus series. In this video we'll be going over integration by substitution. This was briefly mentioned in the integration rules video, however we're going to be going into much more detail here and going over some examples. Okay, in case you haven't seen that video, I've rewritten out the formula up here. So it says that the integral of f of g of x times g prime of x dx is equal to the integral of f of u du, where we understand u is equal to g of x and du is equal to g prime of x dx. Now, an easy way to recall that du is given by this formula, if u is given by this formula, is to notice that if u is equal to g of x, du dx, if we differentiate both sides of this equation with respect to x, du dx is equal to g prime of x, and then multiplying across by dx, we get du is equal to g prime of x dx. Now, technically speaking, this whole stuff is not rigorous. Okay, you're not really allowed to multiply fractions and differentials around like this, but it does work, and it's the reason we use the notation. So we'll pretend this is true for a lot of these arguments, and it's a convenient way to remember the rules of integration by substitution. And as just another side note, if this is the statement for an indefinite integral, if we're dealing with a definite integral, that is to say an integral with a lower bound and an upper bound, we also have to change the upper and lower bound. A gets sent to g of a, and b gets sent to g of b, where g is the substitution we're making, right? We're making a substitution, u is equal to g of x. So you can kind of think of, when x is close to a, what does u go to? And u will go to g of a. And similarly, when x is close to b, what does u go close to? And u will go close to g of b. Okay? So I think this understanding of it is kind of a bit messy. So I think it's better to go over some examples and we can see like how we actually go about this organically. Because you don't actually really have to learn off this formula. You just have to understand it's something you're allowed to. Okay? So let's consider this integral here. The integral of x times sine of x squared. Now, in general, I also want to make clear, this isn't like a bulletproof plan. There's lots of different substitutions you can make on an integral, and most of them will make it more difficult. However, if there's an obvious substitution, or I say obvious, if there's a substitution that seems like it would simplify the problem, it's often a good place to start. So for example, this is the integral of x times sine of x squared dx. This is an integral we don't really know how to solve. It doesn't look like any of our easy examples. It's not a linear combination of them or anything. So what do we do instead? Well, we could look at this and notice that there's a sine of x squared. Now, we don't know how to integrate sine of x squared, even if there was no x out in front. So we really need to do something about this. And the way we'll do this is we'll substitute away the x squared. Because if this was just the sine of u, then at least it would be a simpler problem, okay? So let's let x squared be equal to u. Okay, that's the substitution we're going to do. And notice that x squared here is actually taking the role of g of x in our formula. But like I said, I don't really like to think of it in those terms. So from here, we'll notice that this means du dx is equal to 2x if we differentiate either side of the equation. And then by some fuzzy logic, we can say that this implies du over 2x is equal to dx, okay? And we're also going to ignore problems if x is equal to 0 or anything like that. Because we could just make the substitution du is equal to 2x dx, okay? From here, we're just going to make a bunch of substitutions. Okay, so this is the integral of x times the sine of u. Now, it should be noticed that we don't actually really want x's and u's kicking around, but fortunately, we'll see that the x's will actually disappear after this step. We don't really want to be working with x's and u's at the same time. You can't really integrate something that's got both x's and u's in it simultaneously. But if we substitute out the dx here, this dx becomes a du over 2x. So the x's cancel, and we're just left with a half here. So this becomes equal to the integral, well, 1/2 the integral of sine of u du. And this is just going to be equal to minus cosine of u over 2. And that's our answer, because we can integrate sine of u, okay? So I hope that makes sense to people. The idea of the integration by substitution is to reduce our integral to an easily solvable integral, okay? And then the answer will be valid at the end. Now, we do need to make the point here that our answer is in terms of u, and we don't want our answer to be in terms of u. So we actually just make the substitution that u is equal to x squared, as we said up here, right? So you usually have to substitute back in at the end what your u is equal to. So this is equal to minus cosine of x squared over 2. And you should be able to verify that if you differentiate this, you'll get this function. Okay, so that's the idea. And I'd like to, again, emphasize that we don't really rely on the formula for this. We instead just make some observations and some loose algebra, and the kind of rule just falls out and our problem is solved. Okay? But the idea, I would emphasize that when we're talking about integration by substitution, this is kind of the step you should memorize, and also at the end that you have to substitute back in. But this is kind of where all the action is in solving this problem. Okay? And let's also make the point that if there was no x out in front here, this whole problem would have been impossible. This method wouldn't have worked. We'd have been left with a sine of u divided by x. We'd have had to kind of leave x equal to the square root of u or something like that. And then that integral wouldn't be very easy to solve either. Okay? So it really is nice that this integral does work out. And often they won't if you just try and do it like all the time when it's not really appropriate. Okay? Now let's move on to the next question. This is question B. The integral from 0 to 2 of 5 times x plus 2 all raised to the power of 20. Now this is technically just a polynomial, so it would be trivial to technically expand it out using the binomial formula and kind of use our notions of integrating polynomials immediately, but we can actually be smarter than that, because we notice that if we let u equal to 5x plus 2, then it'll just be like, this will kind of look like u to the 20, and we can integrate u to the 20 very easily without having to do any difficult bracket expansions. Okay, so this would be equal to u is equal to 5x plus 2. And now if we differentiate each side with respect to x, we'll see that du is equal to 5 dx, because du dx is equal to 5, right? Because if we differentiate this, we get 5. Or let's just say du over 5 is equal to dx. And now let's go and make all our substitutions. So this is the integral from 0. Well, actually, that's not write that down yet. So 5x plus 2 is equal to u, so we'll write down u to the 20. And dx is du over 5. So let's put the fifth out in front. Now, the only thing we need to be careful of is these upper and lower bounds. What happens to the upper and lower bounds after these substitutions? Well, we just substitute in basically our values for x. Technically speaking, we consider x that is close to the lower bound, but for this case, we can just substitute it in. Okay? So we take x equals 0 and u is equal to 2, so our new lower bound is 2. Remember that this is, of course, our g of x. So this gets sent to g of 0 becomes g of 0, which is 2, and 2 becomes g of 2, which is 12. So overall, our answer is 1/5 u to the 21 all over 21, evaluated between 2 and 12. So this is equal to 12 to the 21 minus 2 to the 21, 2 to the 21, yeah, all divided by 105. Okay? And we can't really expand 12 to the 21, so we'll leave the answer like this. Okay? But again, notice in this time, however, because we're doing a definite integral, we actually don't have to make the substitution at the end. Because we were careful with our bounds, we changed these bounds, we don't have to do it at the end. If you don't want to change the bounds, I believe you can just, if at this point you substitute in x is equal to 5x plus 2, you can keep your original estimate. You can keep your lower bound at 0 and your upper bound at 2, but you have to be working relative to 5x plus 2 instead in here, instead of the u. You have to substitute in back in your x's. Okay? So now on to the last one. The integral of x squared divided by 1 plus x cubed all from 0 to 1. Okay? So the idea with all of this is trying to identify which substitution you want to make. Now, I know immediately which substitution I want to make, but let's just consider some substitutions we could make. If we let u equals to x squared, because there's an x squared over here, we might want to get rid of it. That's going to be no good, because down here we have an x cubed, and this will become like a 1 plus u to the 3 over 2, and we'll get like a division by x when we bring in du. That's not going to work out very well for us. We could try u equals x cubed, and that's going to work out pretty well for us, because du in this case, I'll leave it to you guys to verify this, but du is going to be 3x squared dx. So then we'll eat this x squared up here when we're combining it. We can combine this x squared basically into a du with the dx. However, we'll be left with a square root of 1 plus u below the line. And that looks a little messy. So instead, we're going to make the substitution u is equal to x cubed plus 1. So we're going to do 1 plus x cubed. And it'll have the same differential, but it'll get rid of the thing below the line. It'll just turn into a square root of u, which is a lot easier. So this is equal to the x squared plus dx. So x squared dx is equal to du over 3. So we got a third out in front. A du is all we've left above the line. And this becomes a square root of u below the line. And we just need to be careful with our bounds. When x is equal to 0, u is equal to 1. When x is equal to 1, u is equal to 2. So our answer is 1/3. This is u to the minus a half. So it becomes u to the plus a half divided by a half. If we remember our power rule, it goes from 1 to 2. So this is equal to 2/3 times square root of 2 minus 1. Okay? So this was the integration by substitution video. Hopefully it made sense to people. And I hope to see you guys next time where we'll be covering integration by parts.